Great. So thank you, Eleni. It's finally I came to see your group. Very successful group. Got it. I know you're recording. That's correct. Good afternoon, everyone. It's Friday afternoon, so I think everywhere in the world is that time of the week that you are excited about something for the weekend. So I'm gonna try to share in the next 40 minutes something exciting for related to research and maybe complementary with the work that you are doing. It's also an opportunity for you to see the work of other students or other researchers doing something, I think, complementary to the work that you do. The presentation is for the work that I do at the University of New Mexico. Is part of the United States. For you, those of you who think is Mexico, is on the southern part of New Mexico. Yeah.
So we weren't counting on the drilling right now.
So put this on.
Maybe you should put it on.
And whatever we do with the mic and everything, no worries. Okay. So thank you, Paul, for teaching me this, but I forgot already. I think it's this way.
Right.
What about now? Great. So I'm affiliated with 3 other departments. The reason I got cross-affiliated, this may be interesting for you, is for legally being able to be a PhD advisor or master advisor, you need to be affiliated with that department. It's politics of the university. So if I have a very interesting part that is multidisciplinary, unless I'm affiliated on electrical, the electrical students cannot work for a degree. So then I joined electrical. Then I got a mechanical student. In order to be their advisor, I had to join mechanical. And then I got a computer science student. And then I had to join computer science. So it's not that I am that clever. It's that necessity to supervise them. To be the chair of the PhD, I need to be cross-affiliated. This is the group that, let me see if this is gonna work. I just try. This is when I got promoted to associate, so that was in July. Not everybody here is in my group. I have 2 collaborators from the hospital that are doctors working in emergency department. We're doing augmented reality for emergency room, emergency in the mountain, emergency rescue, and emergency climbing, because we have a lot of mountains where you have real, I mean, you have a lot of mountains here, where you have a real need for implementing a scanning of cracks, not in structures, but on people, on real-time hands-free. And also some visitors from Taiwan National University. So not everybody there is in my group. We have high schoolers, but not middle schoolers yet in the group. So we're the children of one of the doctors. I presented this on the Mars workshop. I think not everybody was on the Mars workshop. So this is maybe 2 minutes that summarize areas of interest in the smart management of infrastructure. Augmented reality, we've been working on that probably since my first year, second year, 2016. We work closely with Chuck Farrar and David Mascarenas in Los Alamos National Laboratory. I firmly believe that the problem of infrastructure will be solved with a human in the solution. Human infrastructure interfaces will enable to advance, engineers. I will mention today several times, engineers are human. We are humans. So we need not to forget that part and bring that human component to our decisions, our algorithms, our machine learning, our control. It's good to have a human on the loop. My background, as Professor Chatsi mentioned, is a lot of 10.5 years in the design, construction, and inspection of railroad bridges. So I try to bring my knowledge on the field to the research that we are doing now in the SMI lab. The other area that I'm interested in is fabricating sensors. So in my group, everybody has to learn hardware and software in sensor fabrication, and we have these low-cost, efficient, wireless, intelligent sensors. My background is on bridges, but bridges are kind of boring. They don't move too much. So we put the sensor in a rocket. In New Mexico, there is a different culture. So it's very normal to have a rocket club and fly rockets every month 10,000 feet on the air. Last year, we participated in a NASA project where we put one of our sensors 120,000 feet, which is 40 kilometers on the air. So we are interested in local sensors. Something that I think you're doing on the group is neuromorphic sensing. We are using a different approach, event-based. I mean, this is something very interesting these days. We're trying to use what is going on this event-based, and also we are interested in the nonlinear stabilization. Is something that Eric Robbins has been working recently on. Daphne oscillator and having some stabilization. That was his work on the lab. Also, I'm working with the cyber physical system. I'll talk about that, and the topic of this human interface with dynamics, enhancing the humans overlaying the dynamics on the experiment or maybe on the field. This is I actually for the first time this spring teaching model analysis with showing the mode shapes on the class on the first, second, third mode. I mean, we do that on MATLAB, but it becomes more real when you actually see the cantilever being on, 318 hertz, first, second, third mode, and you see it in front of you. Actually, I wrote the whole of this. I forgot. They are on the office. So, Elijah, for the last 2 years, we've been working with this robotic AR interface. Originally, it was for additive manufacturing, and then we get a step back and make it more fundamental how to interact with activities with the interface with augmented reality. So that's going to be the topic of today's talk. Finally, we're interested in some, again, overlaying this augmented reality with artificial intelligence, this crack detection that you can see hands-free real time. And that's been the interest with the hospital, where you can actually do it for cracks in humans because it's the same algorithm actually. What we do different is that we do almost real time. So we just got the paper accepted last week, so I can send that to you. Okay, so why is important to be multidisciplinary? You have opportunities to work in areas that you never thought before. I never thought I would be doing cybersecurity, but we have this interest from the Navy to train cadets in cybersecurity. So I told them, hey, my background is more in structural health monitoring. If you think it's important for the defense to learn about SHM for the cadets, we can do that. And they agreed. So we've been training these 6 cadets: Daniel, Valenzuela, Dudney, Josh is a military Marine. And then we have Connor and Tim. They fabricate all these sensors. Another aspect of our research, we are very interested in diversity and inclusion. So we've been working with a Native American Pueblo where they are actually conducting SHM their way. So we believe every owner should have the power to decide what sensors, where to put them. In this case, Aliciano and Lauren, they're from Oak Wing. They are the members of the group that have been participating on this SHM center activity. Okay, so with this intro, we're going to move to the topic of today. I will motivate it, talk about AR, some introduction about this human-on-the-loop control, and then some interfaces of interest for robotics, which I think is new from what I presented last March on the Mars workshop. I think it's good to contextualize in engineering tasks. It could be research, it could be some decisions out there, experiments, or something that is happening that you want to measure or to understand structures, responsive structures. So we would like to measure something, we would like to control something on our experiment, or we could probably like to do that safely. Maybe we're talking about vibrations, maybe collection of data on the field. I think you're doing a lot of wind monitoring, so maybe you cannot access your facility or your structure. So on this context, that's what I'm talking about, engineering task. It could be that you do it on the lab, maybe actuators, or it could be a structural control, or it could be that you do it on the field, where again, you need to collect something out there that is related to safety or structural health. So in this context, I am interested to explore if the data can change human decisions, which was my motivation to go back for the PhD, because I realized if I give sensors to the railroad for free, they don't use them. Even I have to pay them to use them, they will not use them. And I understand if I give them the data, they will not change their decision. So I got interested, how can we change human decisions? What make human decisions to change on the context of structural health monitoring? So I think the interface where the engineer can transform the input will be valuable for the monitoring cycle. If we can understand what data makes the change of a human, then we can improve the algorithm or the value of our algorithm. And if I can provide that data that change the human decision, maybe I found what is of value to actually repair or maintain or prioritize our infrastructure. So that was my motivation. This picture is with David when we got the HoloLens in October 2016. It was the first time. So we went to Santa Fe and we just got it off the box. I spent 10 hours and this is the best thing that we could do. So we just opened something that we didn't know what we're doing. And now, 6 years later, I'll show you the interesting things that are happening. So I want to interface infrastructure and humans with sensors for changing human decisions. Engineers don't like to talk about this topic. So I understand how you're feeling right now. We don't like to talk about humans. We don't like to talk about behavior. We think that has to be removed. We have codes and we follow the code. You don't talk about if you are tired or excited or nervous. We don't like to talk about human factors. But I believe we should, because we, depending on the human, will make different decisions. I want to investigate that. And infrastructure is what we are working with. So I would like to bring the human to the infrastructure connection with these interfaces and talk about this changing of decisions. In the case we're using some low-cost robots and some augmented reality to see that change. I will quantify with using eye gazing. Eye gazing is not new, but with augmented reality, we can collect it. The reason I use eye gazing is because I understand the attention can be quantified. Maybe I can relate that to safety. About 80 to 90% of humans were very visual. We're not like dogs or bats or dolphins. We are following our eyes a lot. And 13%, when we look at things, we're looking at that 13% attention, and then we block that out completely. And that's an interesting area because you want to talk about which information you are collecting. Maybe we can bring that in front of you. Yeah, events outside of this 13 cone or cylinder are hard to perceive. So that's when safety becomes a concern. This is something that I used to convince you of the importance of this topic. When you run your experiment, even if you have your data on your computer, you prefer to look at your experiment and you move your laptop and you put it right there in front of your vibration. Why? Because you agree with me that you would like to see both the analysis and the experiment at the same time. You can do it so well, but sometimes you're even losing that 13%. This is the Daphne oscillator, and this is a sine sweep. So you still try to do it, but wouldn't it be better if we could put that data on top of the structure so we can see both of them at the same time, and we can amplify the information that we're trying to see on the screen, we amplify it on the specimen. With that, we will change the human decision. I will show you. So this is the framework. The reality is measured by a sensor. We have some time delay on that we measure actually in a communication study that we did. And we will have the human looking at that data, maybe changing the experimental parameters. And then with that reaction is how you actually conduct these experiments. But that is not It's a loop, but it's not a real loop. Humans typically trust themselves better than the data, so they want to see with their judgment if the experiment is doing what they want. So they look at the data and they go back to the experiment. Vision is what we do on the laboratory in addition to the data. And I want to combine that with the automation. And the current model is this, looking at the experiment, looking at the screen and going back and forth. And we want to say that if we put them together, you decrease the time, increase the context, and increase the accuracy of your understanding of dynamics. That's our hypothesis. Data, time, and context. So this is what we change. We think when we overlay the hologram and the specimen, we can increase the synchronization between the data and the reality by the human moving the sensor themselves. It's a very simple experiment, so you will get it. You will see the value when I show it. So we can advance better engineering research, and we advance the human-machine senses and understand the reading from sensor or quantify this reading from sensors. And we could use this for control of the laboratory, or maybe on a bigger system of systems that could involve multiple specimens or multiple more complex decisions. But this is the first step. This is very basic step. So you can criticize it. I want to hear from you, and we can improve it together. For those who have not seen the augmented reality, this is with One Tao in Chinese earthquake administration a long time ago. And we had a railroad bridge. We wanted to protect the railroad bridge from an impact. So I wanted to inspect the deformation of the crash beam. And with a time machine, we can collect data before and after. So the 3D scanning can provide you with an automatic index comparing the deformation, just deformation of the bumper being damaged by that hit. And I show this because as we talked earlier, I worked on the railroad for 10 years. So climbing without having to bring your camera, your notepad was interesting for me, and also for Los Alamos. So that's why we did this hands-free approach. This is a through-plate girder, 1 feet scale bridge, which was very nice that we could hit it very hard there. This is a video that Kabe and Ali put together for the railroad to explain augmented reality. So they actually asked me, hey, can we use a video from Microsoft? I said, sure. So this is not, we didn't do it. Microsoft did this one. But it shows a little better. I mean, they're selling HoloLens. And this is more about what we've been doing with the railroad. This was in the middle of COVID. They came and they told us what are their priorities for collecting this measurement data on the field. And we went there, we did some crack inspection on the laboratory, and also they had a training facility. We went back to Albuquerque, and then they told us, hey, we really want to measure rail gauge. I said, well, that's not a structure. I said, well, it doesn't matter. That's what we want. So that way they don't have to bend down there on the rail, and they can measure by putting 2 lollipops and getting the measurement. This is done all by Jack. We've been working with the University of Kansas. They are very interested in fatigue cracks for the highway, critical fatigue elements, and this is a combination of computer vision with the AR. We just went there actually last week, and we collected real bridge. This is on the laboratory. This is the application from Kabe on concrete cracks. This is the WGE. I still carry this from my industry days. If we could do that automatically without the crack gauge, and that's what the paper is in automation and construction from last week, so it should be still at the top of the recent published. It's 0.5 seconds. It's very, very new. This is a real-time human observation of the crack. We are interested on the eye gazing also for training. So we've been developing this Air Force at the beginning, but now we're looking into bridge, where you can not only learn from the expert people, but also you can train new people to follow certain inspections. It could be that is very good for the first few months, but also it could be that when you want to learn alone by yourself, you can get a score by covering a certain area, and then you know you did a good inspection or not. This was done by Saika. She's also working in industry, so maybe that's why she is interested on this eye gazing. So these applications are more related to what you are doing, some vibration observation. This was done by Marlon during COVID on the little lab that he did at his apartment or his house. I was interested in reference-free displacement, but the railroad told me I would like to see on real time when the train is crossing, I would like to see the displacement in front of me. So that's what we did in COVID. To clarify, augmented reality is 100% about coding. There is nothing more. So if you like coding 100%, I encourage you to work in augmented reality. If you like it 50%, don't do it because it's 100% programming, but it's a very good area if you're looking for something new. As is a very good area, but it's mostly programming. And the other one was for safety, where the railroad told us they don't want to. When you have this 13%, you don't want to have tripping hazards. So that's why we have this rail identification. Okay. So the framework is we have this local sensor. This is actually this is the $100 version. I think now it's 50, but this is from 3 years ago, Lewis 5, where we have a wireless unit. We only provide the power with the USB, but the communication is all wireless. We could have a little battery added to the sensor, but we don't need to do that on the lab. So everything is wireless except the power that we don't need to have the battery charged for laboratory experiments. And with this, this low cost, we can connect everything with Arduino. We don't need to have a better sensor than this. So we like to fabricate our sensor. So that's why we use the Lewis. The Visual Studio Unity and Arduino, we combine it together, and then we provide this real-time interface with your vibrations. And we use Microsoft HoloLens. We get $0 from Microsoft, so I'm not saying that that's the one that you should use. What we do can be used in any other platform. And we like to create this control with the human, where the input is your hand or your DAQ is your brain or your vision, and you have a reason to change your frequency input, and then you will see the response, and then you continue changing it. So I like to say that humans are good in the engineering process or engineering decisions. It's good that we have human in the engineering decisions. That's just my opinion. So then with the augmented reality, we can enhance or help this controller to be better. Increase engineering awareness of structural responses and data. We're going to have first an experiment with reality, which is you observing the vibration and making some decision. Then we're going to have the laptop, and then we're going to have the HoloLens and combining the three. I want to compare the three results. Reality, just observing the vibration. A screen, your laptop, and third, only augmented reality. And this is what we do. Typically, we have a vibration. In this case, we use the sensor to see the vibration, but it could be a specimen. And we'll put the sensor in a shaker because we want to control the source of that vibration. And the human looking at this vibration will change the input. So you have an external shaker, and then you change the input. I have a little diagram here. And we will also collect your eye gazing. So we want to see that you are paying attention to the vibration and how you are conducting your inspection more safely. So we also have that eye gazing. The eye gazing is projected on the 3D, and you can quantify with that data. And also you could do some machine learning with the real human component that you say you want to learn from expert inspectors. And with that, you can train new inspectors with the eye gazing data. So we have the MySQL database, and we have everything connected on our network. This is the 3 cases, reality, and this is the eye gazing you can see there. We look into area. We could also look into velocity, but I'm not going to talk about that today. We'll have the data on the screen where you're going to have to go back and forth between your shaker and your screen, even if you put it aligned. And the last one, and you see it's a little worse because it's more over the place than the first one. You're going back and forth. And also it takes more time to understand. And then with the AR, it's comparable to the first one, right? It should be not much bigger, not much smaller. So it's a similar, you're just looking there on your accelerometer, which should be similar than the reality. So This is the little loop. It's a little complex, but I think this is the simplest that I can do. Actually, Elijah did this for his master thesis. So this is our shaker. We control the input we control only frequency. Then we'll talk about amplitude later, but it's only the frequency. This is the data that measures that vibration, and we can observe that on real time. So with our hand, we will look at the shaker and we will change our vibration, and we will see if I am a good controller by comparing my vibration to what the shaker is doing. Later, I will move the robot and I will see the robot moves like the shaker. But first, let's just do with my hand and see for the first step if I can match that frequency better. We do 5 frequencies and 3 setups: reality, screen, and AR. This is one of them at 2 Hertz. And the blue is the shaker, which is a low frequency, so the Arduino is not so great for that one, but it's good enough for our frequency domain. So that's why you have this strange data here. We are very comfortable looking at this data. So I'm just telling you, it's good for what we're trying to do. And then the black is well, it's not my hand, it's the student doing the experiment. You can see how humans are already much better when you move them at low frequency. That's an important thing that I learned on this research that I didn't know before. Humans are very good between 1 and 3 Hertz, better than shakers and better than sensors. At that level, we are very well designed. When you go a little higher, then you cannot compete, but we can do a much nicer vibration. And in the case of 2 Hertz, this is the amplitude that I was telling you about. It's interesting how with AR, we can kind of stay at the same level of amplitude, which we didn't expect that to be the case. When you don't have AR, you just try to follow, but you don't see how you should be moving. So that was interesting for us. I'll show you the 15 experiments here on the time domain and the frequency domain. The vertical line is the shaker or the sensor on the shaker. The blue line is the researcher. And you know, one is not so good because it's low frequency. But overall, I mean, I was very impressed. I'll show that it's 0.1 Hertz ever when the human is trying to match the shaker. And as you can see here, they become very, very close in time. We also did the time delay. So this is the time delay here. Reality, the AR is competing with that. Separate the screen, not so good. For the frequency Hertz offset, you can see this. This is 1, 1.5, 2, 2.5, and 3. So you can see at this level we are a little better. This is the region of interest. We are getting even a little better than reality. When you see the data, you become better. And the amplitude, I think this is the amplitude. We are also becoming a little better, comparable, except the 3. The 3 is, again, you're getting out of the comfort of the knowledge part where the humans are good with vibrations. So we increase the safety and we can synchronize a little better with AR with a better awareness of reality on this output and hand vibration. With this result, we thought, why don't we bring a robot into the equation? Because robots can access locations or also can do repetition better than humans. So we want to just help the robot, and then the robot can do things for us that we don't want to do ourselves. And it's good that we have automation for many good reasons. So we don't want to remove the robotic or the fundamental value of the robot. We like that on our activities. So we like robots. We to reduce some complexity on controlling the robots. One, this is the Xydon. It's I think $600 Xydon. So this was from Professor Fierro. We could use it for the first types. And with $600, we could do the connection between the AR and the ROS controller. And actually, you can do all of this in MATLAB these days. So it's very much easier than maybe 10 years ago. And when we connected this, I will skip, we're gonna use a more advanced robot, it's a Kinova Gen 3, which is a 7 degree of freedom. This, we're gonna use it just for vibrations, but also has a, for those of you who like computer vision, it has an AI that can help you to grab things in an intelligent way. And what we like to do is to deploy sensors and also to control vibrations. So I will show you how we did these two things. And in this case, we then show it to the Japanese Rail Central. They came to see how we do this, and there's some interesting applications for the structural and railroad engineering. So MATLAB, everything can be done for the most part with MATLAB. We have some MySQL and some real-time database, but everything is controlled, very easy to program. And then we have the manipulator, and we'll show the sensor deployment and the vibration control. So the hypothesis here was, can we deploy sensors a little faster than humans or better? And the other hypothesis was, can we stabilize vibrations better than, for some reason, you could observe the floor moving and you would like to move the robot so things don't fall. So that was this could be the shaker, this could be the robot, and you want to move the robot. You want the robot not to move by controlling the vibration that you observe here. So this was the sensor deployment. Let me show you here how this is programmed with the satellite docking algorithm. And then because we don't have that much access to satellites and we want to do more, we did the sensor deployment, which is for many reasons, robots can find a more optimal way to access a certain task. And in this case, we wanted the robot to compete with the human. So this is accelerometer. We're going to see if we have a less of an impact on the surface and if the time for the location of the sensor is better. And what we did is to compare a trained person and a novice person. So this is a first attempt with a novice and an expert, and you can see the accelerations at the beginning is 9.8, and then when it rotates, it becomes horizontal, and that's when we deploy it. And you can see these are 50 seconds for the first time that you do it, and then it comes down when you go with the AR-25. And what we did is multiple experiments to see how the novice accelerates the sensor deployment. But as you can see, from 50 goes to 25. You just have the start and the end, and the robot is much better always. And this is the robot deployment. And these are the results. We're much better. And then this is twice as fast with the learning with AR. Actually, we did another experiment with the frequency where, as I mentioned, we want to move the Kinova at low frequencies by looking at the frequency that you're doing with your hand. And this is, I mean, we have 1 and we have 5. In the experiments, we have, I think, 0.5, 1, 1.5, and 1.9. And we like the Kinova to move so that we could be a controller for some, it could be seismic, or it could be in the sea, or it could be some situations where you believe the human could have a better awareness of what's going with competing with other sensors, or it could be complementary. We don't need to compete. So in this case, we have the observation of the frequency, and we try to see if the robot can match the frequency that we see on the shaker. So actually, there is a shaker. The human looks at the shaker, and we compare the shaker with the robot that we are moving with our hand. So as I say, we have the 3. This is not a shake table, but that's what we're going to do next. Put the shake table as the input. So at the end, the thing on the robot would not be moved if we do it right. And it could be some contextual information that the human can benefit the machine. And again, we want a team together. And the results are, again, much better than we thought. And this we just did this summer. So I'm very excited about bringing that to the large shake table. And I think I have the results here. Again, for the Arduino, we don't worry too much about those time histories. The 0.5 is give us that problem, but you can see the 1, 1.5, and 1.9 are very, very close. This is the human controlling the robot. The vertical line is the sensor on the shaker, and the blue is the one of the sensor on the robot. The sensor on the robot, we're moving the sensor of the robot with our hand. So in general, very, very good controller. And I think this shows without AR, we just look at the shaker, and with AR, we look at the shaker with the data, and we get a much better match on the robot response compared to the shaker input at low frequency. The last application is for the field application. I have maybe 6 minutes. I will get it so we can have more questions. In Los Alamos with Chuck Farrar, we work. David is a very creative man. So we wanted to do tap testing for, actually say, let's do it for your railroad bridges, sure. But then the DOT came because we have a lot of mountains and the alleys and everything. So there are a lot of surprise rocks falling into the road. So they send people to inspect the rock frequently. So it's basically something that SHM could do a very good service. So you just know when it's about to fall, and then you just call it and you remove it. So it's kind of a, you could call it MBE or something, but they just do it people tapping. So what we did is to create a robot that can interrogate these rocks and inform what is about to fall before it happens and falls into a gutter block, a road, which can isolate the people there. So then from 2016, we brought it to the ground, and then we decided to control this robot with AR. So we have this interrogator. We do some machine learning with the sound. So we classify what is healthy, not healthy. So we do that with the sound, which is a very clever way to do it. And then with the robot, you can do that at the same energy, the same distance, and as many times as you want. What we identify is that it's a little unsafe to collect this data on the field. So we created this sonar that tells you remotely how close you are to the rock without you having to be on the shoulder of the highway, because it could be cars are running while you're doing this experiment. This is the work that we did on the before AR, actually, because we had the snow, we had to put this little box, and actually also we're looking about the future. And this with machine interrogation, machine learning, you can train and compare and classify bad rock and good rock, and then you can decide what rocks you want to take care of for your road. So this is what we did. You know, you can see Roya is right there. Now she's postdoc at Nebraska. Imagine you are investigating the rock that is dangerous and the rock falls on you. You are defeating the purpose, right? So we decided it would be good to have this separation between the robot and the human controlling the robot with AR. I have the sonar telling you where to go, and also increase the safety while you conduct the experiment. And we did that this summer, so that's new from Mars. This is the Tijeras, New Mexico. This is Eric and Elijah. Ronan, he's in high school, so we like to work with high schoolers in our group. We have 3 high schoolers this summer, from 15 to 17. So very, very useful. I mean, he went to the field multiple times. And this is the Brutus in action with eye tracking. We have here, you see Elias here is not so safe. So I hope I don't get in trouble. But after we did this, I said, you shouldn't be there because, you know, you're very close to the line. So when we incorporate the laser, he went to the other side of the road. So that way, you know, you are not exposed to the traffic there. But as you can see with the laser, he can know how close you are to the wall. And you can actually make the robot to stop at the distance that which he did at, I think, 20 centimeters. So you have always had the same energy when you interrogate with your tapping. And because we're looking into the safety, we did this eye gazing, where it shows that when you're using the AR, you're more focused in your activity. You don't feel you need to be chasing your thing. You're just controlling, you're observing the success of your control. I will skip through these results. Basically, they show the ability of the laser to go to that distance, and the time on controlling the robot is increased with the AR deployment efficiency. And to conclude, I know these are a lot of new ideas here, so I want to hear from you what you think. I'm very curious. Some things that we're working on the future. I mentioned Brutus, we're interested to take it on the above water and below water. We have an active project that is looking into these mechanisms to target something that is hard to access for humans. Below water, we want to do it. And also above water, maybe the wind towers that you have in the middle of the ocean. This is with the ONR. This is what we did in December. And maybe I showed this on Mars. I don't remember. I don't know if we saw this last time. So this is with NSF Rapid. They've used this for emergencies. We brought it to our swimming pool at the university. And we did some preliminary studies on the tap testing. And then we went to a dam, actually, to a lake to test it there. So in conclusions, I want to emphasize we like humans to synchronize reality using augmented sensor data communicated with this low-cost sensor with augmented reality. We show that augmented sensor data with control of experimental parameters for informed decisions in the lab, decision-making in the lab. We provided a first-step control of several motor devices with AR and Lewis, and develop advanced control applications for robotics to help novice users understand complex control of the Gen 3, the sensor deployment and the vibration of the Gen 3. That's our complex robot, our Kinova. We are including the sonar to inform inspectors of the distance so they can interrogate their machine learning tap testing, even if they're not close to the rock face. With that, I appreciate your time and your attention. I'm looking forward to your comments or suggestions. Thank you. Okay.